So, have you ever really wondered how an AI actually learns? I'm not talking about some magical flash of insight, but the slow, step-by-step process. In our last explainer, we saw an AI get better with feedback. Well, now we're going to slow everything way, way down. We're going to watch exactly how that improvement happens inside the machine, one tiny mechanical adjustment at a time.
Okay, before we dive in, let's get one thing straight. We are not about to witness a moment of genius. Nothing intelligent is going to happen suddenly. What we're about to see is a slow, gradual, almost boring process of change. And honestly, that's the real secret to how this whole thing works.
Here's how we're going to break it down. First, we'll look at the machine itself, what a neural network physically is. Then, we'll watch it make its very first completely random guess. After that, we'll zoom right in on those tiny little adjustments that are at the heart of learning. And finally, we'll see how all those little changes add up to create the right answer.
So let's start with the basics. What is this machine we keep talking about?
This is it. And I want to be really clear, this is not a brain. It's just a set of connected units, or neurons, that are organized in layers. You've got your input layer where the information comes in, one or more hidden layers in the middle doing all the processing, and an output layer where the final answer pops out. All they do is pass numbers to each other. That's it.
Now, here's where it starts to get interesting. Imagine that every single connection between these neurons has its own little volume knob. We call this knob a weight, and it's literally just a number. If the weight is high, the signal passing through gets stronger, giving that connection more say in the final outcome. If the weight is low, the signal gets weaker.
And there's a second set of knobs you need to know about. These are called biases. Now, a bias sits on the neuron itself, not the connection. Think of it like a little push. It can make a neuron more eager to activate, or it can make it a bit more reluctant. It kind of shifts the neuron's default setting.
So if you remember one thing from this section, make it this. When we say a neural network learns, all we really mean is that it's systematically changing these thousands of little numbers. It's just turning all those tiny knobs, the weights and the biases. That's the entire process.
Okay, let's move on. We've seen the parts of the machine. Now let's see what happens when we switch it on for the very first time. We're going to give our network a really simple task. Finish this sentence. Now, you and I know the answer is Paris. The network, on the other hand, has absolutely no idea. It knows nothing. And why does it know nothing? Well, it's because, to start, every single one of those knobs we just talked about, every weight, every bias, is set to a completely random number. It's a blank slate, but it's a very chaotic and jumbled one. So, we feed our sentence in, the numbers flow through this random maze of connections, and out comes the answer, dog. Now, I want you to pause on that. This is not a mistake. It's not a bug. This is exactly what a machine with random settings is supposed to produce. Total nonsense.
The system then compares its output, dog, to the correct answer, Paris. It doesn't understand what these words mean, of course. It just measures the mathematical distance between them. That difference gets boiled down into a single number. We'll call it the error. Let's say in this case it's 92.3.
And this part is absolutely critical to understand. The network does not get a helpful note saying, hey, dog is an animal, but Paris is a city. It gets zero explanation. The only piece of feedback it receives is that number, 92.3. It only knows how wrong it was, not why. So now for the main event. How on earth does the network use that one single number to get any better? This is the very core of the learning loop. The system works backward from the error. It looks at a connection that played a part in producing the wrong answer, dog. Because this pathway led to a high error, the system gives its weight a tiny, tiny nudge downward. Its influence gets just a little bit weaker, maybe from 0.71 down to 0.70. At the exact same time, it identifies a different connection, one that, if it had just been a little stronger, would have pushed the output closer to the correct answer, Paris. So what happens? Its weight gets a tiny nudge up. Its influence grows just a bit, maybe from 0.45 to 0.46. And let's be super clear here. Each one of these adjustments is microscopic. A single change from 0.71 to 0.70 has almost no noticeable effect on what the network spits out. It's the slow accumulation of these tiny changes that actually matters. And it's not just the weights. The biases get adjusted in the exact same way. If a neuron being more active would have helped, its bias gets nudged up, making it a little easier to fire next time. If it contributed to the error, its bias is nudged down. It's just a gentle tilt. You're not
adding new facts, you're just changing the system's default tendencies. So we've seen one tiny little nudge. Let's zoom out now for the final section and see what happens when this exact process is repeated thousands and thousands of times. This is the entire learning loop right here. Input, output, calculate the error, make a tiny nudge. And then you just repeat, and repeat again, thousands upon thousands of times. Learning isn't some big event. It is simply the accumulation of countless tiny adjustments.
So after thousands of these loops, we run the network again. Now the output might be something like city or maybe London. It's still wrong, right? But notice how it's getting closer. It's more relevant. That's because all the pathways that led to complete nonsense, like dog, have been slowly weakened, while the pathways related to places and capitals have been slowly strengthened.
And then finally, after many more thousands of iterations, the word Paris comes out. But why? It's not because the network suddenly understands geography. Paris wins because the grand total of all those tiny nudges has literally reshaped the network, carving a path of least resistance where the numbers just naturally flow to this correct results. I think this analogy just captures it perfectly. Learning is like mechanical stress. The network is slowly, gradually bent into shape by the constant pressure of that error signal, little by little, until it finally holds the form that we want. So what's the big takeaway here? It's just these 4 simple mechanical steps. Weights change, biases tilt, different paths compete with each other, and in the end, one answer eventually survives.